Here are several problems where we make connections between heat and enthalpy of reaction, paying attention to units and signs, kind of in all the different ways that this can look. We can really make lots of different connections between this equation, Q equals mc delta T, and the definition of delta H, where we use delta H to find things about heat or temperature, or find things about heat or temperature to connect to delta H. So we want to be very comfortable with that back and forth conceptually, and very important with that back and forth in terms of calculations. So we have our first scenario, which is sodium placed in water. We may know or remember that that's an explosive reaction that gets very hot. When that happens, it would cause the solution to increase in temperature. So anytime we see an increase in temperature or we see two temperatures, that's our clue that we're looking at heat in terms of Q equals mc delta T. The Q is going to be calculated. The M, 200 grams, it says 200 grams of solution, or enough water to make 200 grams of solution. I did not include it in the wording of this problem, but it does appear in the wording of a few of the coming problems that you would have to be told the specific heat. Previously, I used 4.18. In these problems, I used 4.184 just because the source that I had copied these problems from used that number. It's most common in an AP problem that it gives you 4.18, or sometimes it even rounds that to 4.2. But we have 4.184, we see our temperature change. So that 200 grams of solution, because of its temperature change, absorbed 29,300 joules of energy. It absorbed 29,300 joules of energy because the reaction released that much. So when I come down here to my delta H and I plug in my amount in kilojoules rather than joules, I have changed that from a positive to a negative. There is not a mathematical step that forces you to do that, or there's not an equation that's going to show you that that sign needs to change. There's not a reminder. You just need to remember, this is information about the surroundings. This is information about the system. So then my kilojoules over moles gives me my kilojoules per mole. And it's very important with the wording of this to have that as negative. The second scenario here has a calorimeter. We've got some sodium hydroxide and some hydrochloric acid. It gave us a temperature. It gave us a final temperature. Once again, Q equals mc delta T. It says assume the density and specific heat are the same as that of water. So that's maybe a little bit tricky here, but that's our clue for two things. One, that we're going to use 4.184 as our value of C. We know what our delta T is, but our M, and it wasn't an issue up here, but right here it is. The M is the total mass of solution. This we will practice for sure in the lab, but it's maybe the easiest place to make some mistakes. It's not just the sodium hydroxide that's heating up. It's not just the hydrochloric acid that's heating up. It is both. All 200 milliliters, which in terms of density, we know is 200 grams. So it's the entire solution. If we're thinking about a solid and a liquid, it's the entire thing there. We multiply that all out, we get a little bit more than 5,000 joules. When it asks per mole, up there we knew our moles, but here we get moles by connecting the amounts that they give us. They give us molarity, they gave me volume, so I can find my moles. My kilojoules divided by my moles gave me my heat, and once again, it went up in temperature. That means the surroundings gained that heat, which means the system lost that much heat. So that much heat lost per mole gave me my heat per mole. The positive and negative sign is super important. And we'll see down here a mistake that I am fixing before we even get to it. This is a thermochemical equation. The only difference between a thermochemical equation and a chemical equation is that it includes a value for how much heat is either gained or released. Sometimes it's written as a delta H value. Sometimes it's written within the problem as a joules or kilojoules value. And we see that this one gives off heat. Heat is a product which means that it's exothermic. We are making heat or releasing heat, just like we are making and releasing CO2, and we are making and releasing H2O. From here, we're more or less just doing some stoichiometry or some mole relationships. I can do grams per mole using a molar mass, but then I can also see that 1 mole of this reacts with 5 moles of this to make 3 moles, 4 moles, and 2,220 kilojoules of energy. So the coefficients can connect to my delta H or to my amount of energy or enthalpy, 22,000 or 2220 kilojoules. I divide, I multiply, I get my value, and I already corrected myself here because if it's talking about energy exchanged, it's super important to recognize it is released in this case and it has a negative sign. If we wanted to do something with temperature change, we could go back, use Q equals MC delta T, knowing that the temperature will go up. Probably more than the problems that will follow this, the questions that connect Q equals MC delta T to delta H and delta H to Q equals MC delta T are the most important to practice because of those sign changes and because of the units that we want to make sure we're paying attention to.